I'm pretty sure that all of you have heard about the Internet of Things. So what I'd like to do is focus on some of the research challenges. Maybe for this community it's quite relevant to understand which breakthroughs are needed for these visions that technology evangelists project. So we see all these videos where people from companies go around and explain how the Internet of Things is going to change our lives, make them rich. But from our point of view as a scientific community, what are the big challenges? And that's the main point. And I will focus a bit more on communications because that's my area. But in the first part of the presentation, I will talk more generally and try to pinpoint all the challenges. So I have 4 questions that I hear a lot about. And so I divided my presentation according to those questions. First of all, what it is, what is the Internet of Things, what is not. Then the second question is, why do we as scientists have to care about it? This is something, it's like a technology trend. Why do we have to care about that? And the third question is, how big is it? How big is it going to be? How big is it going to get? Because if we understand this question, then we also master the big challenges behind making this reality. And in the final part, I will try to go through some of these challenges, but I will scope it down to communication networks, smart communication networks, which is my main topic of research. Feel free to interrupt. I think we can try to get this interactive. There will be time at the end for questions, and then the rest of the week and next week also we can interact, and I welcome this. So let's start with the easy part. It's the idea, the Internet of Things is this idea that everything gets connected. The building blocks, it's sensors. What you see here is the ingestible sensor, or some people might say indigestible sensor. You put sensors in a pill, you swallow the pill, and then you get biosignals out of your body, essentially. Then there will be controllers that they're plugged in. This is the Google Nest controller. So it makes sense of the environment, tries to improve the energy consumption and comfort in your house. Some of you may have it in your house. It's a controller connected to the internet. And then there's also actuators. So that's the third building block. In this case, you see here as an example a pump that can inject insulin in your body, can monitor and inject insulin in your body, all that remotely. So this is really not the future, it's more of the present. But the reason why I picked these examples is because we can all see them, and we can see how by using sensors, controllers, and actuators and connecting them to the internet will enable some major other things. So let me just borrow a short video clip from people from Intel who explain what the Internet of Things is in just 1 minute. I think this video will explain it better than I can do. So just listen to this for 1 minute.
IoT is an evolution of mobile, home, and embedded applications that are being connected to the internet, integrating greater compute capabilities, and using data analytics to extract meaningful information. Billions of devices will be connected to the internet, and soon, hundreds of billions of devices. As related devices connect with each other, they can become an intelligent system of systems. And when these intelligent devices and systems of systems share data over the cloud and analyze it, they can transform our businesses, our lives, and our world in countless ways. Whether it's improving medical outcomes, creating better products faster with lower development costs, making shopping more enjoyable, or optimizing energy generation and consumption.
Okay, so what it is about, it's systems of systems, fairly complicated ICT systems. You connect sensors with sensors, sensors with actuators, sensors with computers. So it's sophisticated systems of systems. Then it's about doing data analytics at large, not just in the cloud, but at large. And the third element I wanted to pick up from this video is that has the potential. So they're talking about potential, it's not a real thing. It has the potential to change our lives, and they even put business before lives. But because this comes from a manufacturer who's trying to, I think, put their chips everywhere in the Internet of Things. So I think it's a good opportunity for them. But what it is, that it's so cool about this is the idea that you can build cyber-physical systems. So the idea that you can put sensors, attach sensors to real things, and in such a way get the information from those real things into the internet and make computation. You can attach, as we've seen, also controllers and actuators. So I'll give you just 4 examples of cyber-physical systems to see the magnitude of the problem and the potential at the same time. One is the big cities. We've heard about the big cities, 20, 40 million people living in one place very soon. This is a major problem. So we need to turn big cities into smart cities. And you can imagine having all the sensing and actuation and control capability in a large city with information coming from heterogeneous sources, how complex this will be. But it might be just one way to address this management of big cities. Another example from food production, the idea is that we have issues with feeding the whole world and not just the western part of it, and at the same time trying to avoid depleting the globe of all natural resources. So again, this is an Internet of Things problem, perfect Internet of Things problem, where you can check how much water goes into the plants, humidity, conditions, and so forth, and optimize that. In the Netherlands, there's a lot of farming that is done like that in a controlled environment. And then the big industry, an oil rig, just to give an example, has an excess of 30,000 sensors. They only use 1% of that information, simply because it's so difficult to make use of all the information available. So they do need information. They put the sensors in, but they don't use it. So it's just the question is how to do it for the future. And the last example I have is from the Rotterdam port as a good example, I think, of logistics and complex transportation systems. It's a port that stretches 40 kilometers, and it processes 450 million tons of products. Not all these products are the same thing. Some of these products are perishable. So you really need to have sensors in each of those containers that you see there, and not just one sensor, many sensors, and get the signals out. We just finished a project where we are trying to get signals out of those containers. You can imagine they are metal, they are Faraday cages. And still, we need to get signals out. And there's a lot of signals, and there's a lot of interference. And it's very, very hard. There's high-density networks. So how to get the information, the signals out of that environment, in a high-dense environment, and then the next step is how to use it. So these just 4 examples, but there are many more you can imagine. Now I want to share with you another very short video clip. In this case, it's a recent commercial by Cisco. It's an electro device manufacturer. So they will be interested in connecting as many things as possible so they can sell their boxes. I would invite you to look at this commercial with a critical eye.
This is the cat that drank the milk and let in the dog that jumped on the woman who brewed the coffee.
Brew coffee.
That woke the man who was late for work.
All right, I gotta go.
And drove the car
Driverless mode engaged.
that found the parking spot.
Find parking space.
Parking space found.
That alerted the door that opened the control room.
Hey, Bob.
That secured the data, that directed the turbines, that powered the sprinklers, that watered the grass, that fed the cow, that made the milk, that went to the store, that reminded the man to buy the milk. It was poured by the girl who loved the cat that drank the milk. The Internet of Everything is changing everything.
So the reason why I asked to be a bit critical on that is because I'm a bit negative about this perspective where we have a technocracy, we have life automation, everything is automated, and this is a boring cycle that starts and ends together. So I don't know why they chose to do this commercial in this way. But I think this is quite, Internet of Things is much more than life automation. And it's also, it's domotica, the killer application, so I wouldn't be so sure. What I think it's, this Internet of Things is about having the ability to extend our 5 senses. This is one example where it's much more powerful. So we can have machine vision merged with all sort of information from the physical world, all put together, and you can see it. So it does much more than what we can do. You can sense electromagnetic fields, you can sense force, you can sense all sort of physical elements that you can imagine, and have all of that available for you. So it extends your senses in one word. It extends also our capabilities, so the less able people, for example, or elderly But in general, imagine all the sensors you have in our cars, and if they're all connected with all the other cars, the reaction time of the sensors and controllers that we have and the actuators we have would be so much higher than the reaction time of individual drivers. So it's extending our ability. And the third element I see is very potential when you put together information that is available on the web with information that comes from the physical world. I'll give you an example which is extremely simple. Just to give you an idea, the Google Flu project that just ended, they managed to put together information from people typing queries about flu with their location, so physical information with human-generated information, and they could predict the outbreaks of flus with a 95% accuracy. So this was published in Nature, so it's quite a breakthrough by just putting together two pieces of information. Imagine if you put together all physical information that you can extract from sensing element with human-generated information. It's quite powerful to increase our knowledge. And then if we really want to be even stretch it farther, you can imagine that you can connect all our biosignals, even the brain waves, connect them to the internet, and then improve our knowledge about our body, improve our health and all that. Now, before we get all carried away with all these futuristic scenarios, I think it's better to stop for a second and reflect on some aspect. So let's assume that we are comfortable with connecting everything. I'm not sure all of you will share this, some will have your concerns. So let's assume that we are comfortable with connecting everything, that we're also comfortable with this super big brother thing that will come out of the Internet of Things, will be much worse than the web. Let's assume we also are not worried about this technocracy that controls our lives, and we're not worried too much about becoming addicted. And by the way, all these four things are in the web already. It's not something that will come with the Internet of Things. But the Internet of Things will make all these things really, really worse. Because you have your sensor, you buy it, you plug it in, and the moment you plug it in, this information will go somewhere. You lose control of it. So if you're monitoring, if you're ingesting the sensor pill, it's information from your body that is online. So I'm not sure whether this is going to happen without new policy rules. But let's stop on this direction for a second, because this is too much of a big problem. And let's see why we as scientists should care about the Internet of Things. Well, for one, the issue is that the Internet of Things is a lot of things, and they might actually crush the Internet. So the Internet and the web, it's responsible for a revenue of $11 trillion in just 4 years. These have been counted by somebody somehow. So it's quite a critical backbone for our life in general, not just for financial reasons. So we need to make sure that when we do connect all these little things, we don't crush it. The other aspect, and I will point you to this report, which is just released a few months ago by McKinsey, is quite detailed. If you want to understand more about the Internet of Things, they are explaining the main sectors where there is potential, and they also come up with this figure of 11 trillion. It looks like the magic figure. $11 trillion will be made in a year if everything is done properly. So prospects. But anyway, these are business opportunities that companies are not prepared to abandon, so they want to pursue all of them. Then there are also, it's not only about money, there is also societal problems. These are the 6 top societal problems listed in the European Horizon 2020 research program. There are more, and I'm sure some similar ones will be in Australia and in other countries. Well-being, health, these are very, very important topics that all the countries at the moment are looking at. So there is a potential for complicated systems of systems, including sensors, actuators, and cyber-physical systems in general, to address those major societal problems. So I think it's worth pursuing this direction. And as academics, I suppose here most of us, not all are academic doing research, there are opportunities. One is I just mentioned the Horizon 2020 program in Europe because that's the one I know. There's 80 billion for research in Europe, and about 1 to 2 billion are for somehow directly or indirectly related to IoT. So you can imagine every professor around Europe is competing for those 2 billion. There is also, and that is experience I had from being in a technical university in a fairly industrialized environment, industry is coming back to academia because they do want to get their stake of the Internet of Things, but they don't have the know-how. They don't know about big data. They don't know about network science and all these topics. So they're coming back. So it's an opportunity for us to re-engage with the industry. And well, another important element is jobs. And somebody took the trouble to calculate 4.4 million jobs have been created by data science in general worldwide this year. So it's new jobs, so it's quite potential. And now this translates into academic terms because we do have to set up new master courses, new PhD courses and all that to produce all those people. In the Eindhoven region, it's a pretty small country, pretty small region, is the most industrialized region in the Netherlands. There is a demand for 300 to 500 data scientists per year just from the local companies, and we just can't produce them. So we are setting up new programs, and it's an opportunity, I suppose, for every university. There are data science centers growing up like mushroom in Europe. I don't know here, but pretty much in the UK, there is every university setting up a data science center. So this is an opportunity for academics. That's what I meant. Okay, let's now switch to more practical part of my presentation. Because if we understand how to answer this question, then we understand also some of the challenges that we as scientists can study. So how big is it? Well, this is an estimate by the Trillion Sensor Summit. So they estimate 1 trillion sensors, just in terms of sensors being connected within a few years. But it's not just a consortium. There's also companies, HP and all that they estimate. They have similar estimates. Why is this number interesting? It's a trillion. So it's 3 orders of magnitudes more than the current internet in just a few years. So this is going to be the largest network that we've ever seen, built, according to these estimates, in just a few years. I'm a bit skeptical about how communication protocols can handle these kind of networks. Then the next dimension is complexity. Now we're talking about a number of connections that are for sure larger than the synaptic connections we have in our brain. This is a lot of connection. We don't understand how to manage the brain network, how to understand, even understanding of the brain network. Imagine if we can understand a network of sensors that are randomly placed around by different manufacturers. So this is a complex network, and I borrow here the definition from complex theoreticians. It's the Internet of Things, and you can read also the brain. It's a network where properties of the whole system can't be inferred from those of individual parts. The second important element is that individual components interact non-linearly, and then you have an emergent behavior that's very hard to predict. And the third element that makes the system complex is that they constantly evolve and change. They're very dynamic and they change all the time. So even if you could capture a snapshot of 1 trillion sensors in a network, it will change the moment you have captured it. So it is an impossible problem. It's a complex system. This is, according to this definition, is going to be the most complex network ever. Then data, that's the other element. How much data is going to flow into that? Because we need to understand the magnitude of the problem. Where estimates are for 10% of the whole digital universe is going to be generated by sensors. How much is 10%? It's pretty much like 44 billion bytes generated in 1 month. And it's pretty much the same amount of data has been generated in the web during the whole duration, the whole lifetime of the web. So we generate in 1 month the same amount of information. So it's also a big data problem. But what makes this really challenging is that these data are going to be unstructured from uncorrelated sources, and very hard to correlate sources. And inherently, you're going to miss a lot of data. You're going to have noisy data, incomplete data. And what is also quite challenging for those of you who are working on big data will probably appreciate this element. A lot of this data will only be valuable in the short term. Imagine I have a sensor there plugged in. I will show you a demo in the end. We are taking temperature, light, humidity information from that sensor, and we store it. We did it from 10 sensors. We monitored it for 1 month in our lab. It was 100 gigabytes of data. Do you really need that in 20 years? You probably need some aggregation of it. You probably need some pre-processed value of that. You don't really need all this data. This data might be valuable if you can process it within seconds and do something clever with it. So that makes the big data problem really hard, because you have lots of unstructured data, and you have to do things in real time if you want to do anything sensible. I think I mentioned at the beginning this example of the oil rig with 30,000 sensors, and they only use 1% of this information precisely for that reason, because they can't process it. They don't know how to do it, how to extract knowledge out of this data. Energy. Now here is even a bit more challenging. My estimate is that we are going to need 1 terawatt to power the Internet of Things. How did I come with that, to that conclusion? Well, if you take a Zigbee radio, so just the radio part of some things that you connect, it takes between 1 and 100 milliwatts, depending on what it's doing, just to keep the electronics alive and transmit bits. If you want to do something a bit cleverer, you use a Raspberry Pi, it goes up to 3 watts and even more. So if you just average like 1 watt times 1 trillion, it's 1 trillion watts. Now, how much do you think a state-of-the-art nuclear power plant can generate? Well, 1 gigawatt. The ones that they are being approved for constructions in China right now. So they're not even there. And if you look just at China, they are trying to get approval to have 80 of those approved and constructed within by 2020. So we are very, very short of energy, but the big problem is not just generating that energy, it's getting the energy all the way down to the periphery. So you can have all that energy somewhere in the nuclear power plant, but how can you have it in your sensor, which is located remotely in a forest somewhere? So if I ask you now the same question, what are the challenges? I think we already see the magnitude of the challenges. I think that's where we are at the moment. The proposal of having 1 trillion plus things connected is not going to happen. I don't want to be a catastrophic person, but it's not going to happen because we are hitting fundamental physical barriers of complexity and energy. So I don't see how people can project that unless somebody comes up with a solution to those major challenges. It should be one of us. Yeah? But now I would like to switch to my final part. So focus more on communication problems, because this is the bit that I do more. And ignore some of the other big challenges like privacy and all these things. They are equally important, if not more, because they may stop the internet, but that's not what I do. So let me focus on some topical issues that I look at in my work. But is there any questions so far, or any reaction, because I put some big numbers there. Maybe some of you don't agree, and it'd be nice to, okay. Okay, so let's get into communication problems for IoT. If you look at the internet, it's fairly simple protocol, communication protocol, very, very simple. They've been there for 40, 50 years. They work if you can make predictions of traffic, location, sinks and destinations. So you can make prediction, dimension the network. Telecom operators do this all the time. They periodically redimension their networks, and they can predict a certain amount of peak traffics, and they dimension things so that on average everything is fine, except when there are cascading failures because the predictions are wrong. Now, these fantastic predictions, these fantastic patterns are not going to characterize the Internet of Things. I hope I convince you, because it's a complex system, and it's very hard to extract patterns as visible as this one. So we went to looking at nature to try and steal some secrets from nature. And the first approach we tried was, I mean, of course, it's not just us in the world. I mean, a lot of people are working on this simple mechanism of nature. The first approach we tried is, the question was, can we try the simple mechanisms of nature rather than starting from the complex one? So, the internet is simple. We want some other simple mechanisms. And the first one we came up with is mimicking swarm intelligence. So the swarm computations, they are well-known methods being developed in computer science now for the past few years, but with fairly little application. And I think there could be a very good application of these methods in a high-density, very large-scale network. So let's see what these swarms can do. So you might have seen things like this. They are periodically, they do these things in Italy, in Rome, in many places in the world. And you see here an amazing level of coordination. timing, and also the beauty of this performance. It's all due to coordination. But the trick there is that the communication mechanisms between these birds are extremely simple. So it's not something hard to re-implement in a computer. In fact, these are the main characteristics that we borrow when we start to implement these swarm computations in sensors. So the communication is extremely efficient, and because of that, it's also very easy to implement. You don't need much memory, you don't need much computation and energy to run this. They are very, very simple communication mechanisms. You have self-organization. You've seen the self-organization through the swarms. They adapt dynamically. They can change direction quite fast. They are stochastic processes that self-organize. So when you have a big number of stochastic processes, things tend to go quite well. And you have this collective behavior, the sort of thing that you've just seen in the video, that is the result of extremely simple local actions. So the idea is that if everybody does the right thing, then collectively you have these kind of results. Okay, without going into details of algorithms, just want to show you some results, some data. So what you see here, it's the algorithm. That's why you have epochs. So it's time, during time, these nodes exchange information all the time. So as time elapses to the right-hand side, you see the status of the algorithm. I'll rather point it on this side. Okay, so what we have, these are scale-free networks that we tried also other networks. Essentially, you have the convergence of the algorithm here. So you see that after very, very few computations, you converge very, very closely to stable state. And what you see in color is the rank of the nodes. You can do this also for links. So how important these nodes are for communications, for the communication in the overall network. So in red, you see the nodes that are really important. If you remove the red nodes, you lose communication pretty fast. If you, on the other hand, remove the blue nodes, you can keep communication. You can make communication even more efficient. So if you look at this ranking, what can you do with node ranking? So if you can rank your nodes, if you can rank your needs, your links, what happens is that you can, for example, start from 1 million nodes. That's the largest simulation that we could do without getting into bug problems. So you start from 1 million nodes. You start removing the blue nodes, the ones that are less important, and then you continue removing them until you arrive to a level where you have 90% of nodes connected. The network is still connected because you have removed nodes that are less important for communication. The network is fully connected, but imagine that 90% of the nodes are off, are not needed for the communication. So imagine how much you can save, not just in terms of energy, but spectrum efficiency. So other things you can do, in fact, is a very big problem in communication networks at high density, such as the one in the Internet of Things with 1 trillion nodes, is that they will all compete for spectrum. And if you have 1,000 sensors in this room, it will be common in the future, according to these visionaries, then these nodes with current protocols, they will only spend time clashing with each other, not communicating real data, unless you can find a way for them to decide when it's a good time, when it's a good moment to communicate. Other things that you can do, you can discover hubs, you can discover bottlenecks. This is all network science in the end. So that is an example where you can use network science in the IoT big data problem. Why can you apply network science in this case? Because we are using swarm algorithms which are distributed. Conventional network science would run this algorithm in one computer, which is not useful to address problems for the IoT. I give you a couple of more examples. Cascading failures. Now, if you have a failure, because of all sort of issues that you might have in a communication network, you have a failure and it cascades, you might want to confine these cascading failures. And one good way of doing that is to know which links and which nodes are the ones who are propagating these cascading failures and isolate the areas. Using exactly the same approach, you can isolate cyber attacks. So if you know that an area, there is a cyber attack in a certain area, you do a node removal starting from the most important links and nodes around the attacked area, and you isolate this area very, very fast. So this node removal process that I showed you here was done by removing the least influential nodes. Now here, you want to keep the network connected. But if you have a cyber attack, you might want to isolate it by removing the most influential nodes. So to this end, this node ranking is quite important. How to do node and link ranking in a distributed way for trillions of nodes. That I find it's where we haven't solved it. We have gone up to 1 million so far. Okay. Let's see at something else. This up to now there were the most simplistic methods in nature. What if we want to try and do machine learning? Machine learning is fairly advanced. We can mimic trial and error learning, and you can mimic. There is the math to do a lot of things, but this math runs quite well on a computer. So you need to bring all the information in a computer, I mean the data set, and then you can learn, you can extract models, prediction models out of them. Well, in the Internet of Things, you don't have this luxury. You can't bring the information in one place and do machine learning. So I would say that we need some centralized version of machine learning. Or even better, I would switch from that metaphor of the brain to this other metaphor of the octopus. The octopus brain works like an Internet of brains. So it has been discovered in 2001, and there's a publication in Science that explains it all. Essentially, you have the brain the size of a walnut, and then you have neurons all the way to the tentacles. So it's a hierarchical brain. And they could prove that by doing so, the octopus can actually learn how to open a jar by just doing trial and error on the tentacles, on the neurons on the tentacles. So without intervention from the central brain. And that's exactly the idea we are pursuing in the context of the Internet of Things, or machine intelligence for the Internet of Things, where you do have data analytics in the cloud somewhere, but then you also need some kind of hierarchical fashion, a hierarchical way of doing clever computations all the way to the end. Now here is an example. I actually have a live demo running there, but I will show it at the end so that we don't crash the system. So what you see here is a sensor with 10 kilobytes. It's very big, just for because it makes it easier to do tests on it. But it has 10 kilobytes, so you can imagine this sensor being very, very small. And what you have here is we managed to implement some machine learning algorithms, very lightweight, in an architecture without floating points. So if you just run machine learning on a computer without floating points, it just doesn't stabilize, it doesn't work. So we had to do all sort of tricks to make it run, to make some extreme learning and some other simple interpolation algorithms on such a small architecture. It was quite challenging. But what's the value of that is that you can then do things such as smart anomaly detection. In this example, there's two LAD here. I'm not sure whether you will see them when I play the video. There's a green one and a red one. That they show you the internal status of the learning algorithms. So green means it's learning. Nothing means he has learned a pattern. And red means, oh, it's an anomaly. So if you can detect anomalies in this way without programming any thresholds, that's the idea. Otherwise, there's no, I mean, if we were to program the threshold, we had to consider for the particular environment what the conditions of anomaly would be, and programming 1 trillion sensors and reprogramming them and changing them, it's not doable. So the idea here is, can we program the system so that it will try to detect patterns, and if these patterns are sustained, then it doesn't have to transmit anything, because essentially we have normality. And if anything changes, they start transmitting. So here what you see is the algorithm goes through the beginning, through a self-calibration. The pattern here is this repetitive tapping. And now it's learning, it's flashing green. It's learning the pattern. Now if we stop tapping, it flashes that as an anomaly now. And if you start again the tapping, because it remembers that the normal condition is the tapping one, it is flashing like normality. So it is a pretty simple thing. I mean, it might not be so impressive, but it was, for me, it was quite a big step, because now we can use different patterns, different tapping, different conditions, different levels, and the system will detect some level, okay, not any pattern, Of course, the system is pretty simple because of the memory and limitation of the architecture of the system. But it can detect some pattern, and by doing so, doing some simple machine learning and some simple pre-filtering is the sort of stuff that happens in a way, if you want, in the tentacles, in the neurons of the tentacles of the octopus, something along those lines. So it's a mechanism that you would combine with something else. I'm not saying that this will replace data analytics, of course, far from it. So this, what I would call miniature machine learning, I find it fascinating, quite an interesting research area for those of you who are into standard machine learning and data mining. It would be good to start collaboration on this, on how to port some ideas, some mathematics into the small world, because that's needed for the Internet of Things. So the idea is that if you combine this simplistic learning mechanisms and the tentacles with proper big data analytics, and you create a hierarchy of that, you might be able to manage much more complex processes than we have today. And well, we can imagine also, on top of anomaly detection, addressing this issue of spectrum efficiency. Now, today, communication is deterministic. So if you have something, you program it, and you decide that it will sample the temperature every 1 minute, it will send the value somewhere to a collector. But this will not work if you have a high-density network. So the idea is, why don't we use some form of anomaly detection combined with the application that is running in the sensor, and try to reduce the transmission time and make sense of also of the environment and decide when it's a good time to transmit. So you can apply the same form of pattern recognitions, so simple predictions that you have seen with the light anomaly detection example. You can apply that also to communication problems. Well, the overall aim that would be to reduce the footprint of the Internet of Things using this mix of centralized and decentralized machine learning. Here I have another example, completely different story on why we have a problem with communication networks in high-density wireless systems. And one of the problems is these 4 elements that are textbook stuff that we teach in computer networks, year 1 students. That when you want to have a computer network, the first thing you need to do is take care of these aspects of layering, abstraction, insulation, determinism. Those of you who teach computer networks will see that you actually have to teach that this is the proper way of doing it. But in an Internet of Things wireless high-density environment, this things is one of the stoppers. I'll give you an example using some video, some work we've done on video, just to see why the network should understand the signals more than it is, and currently is not. The idea is that network should treat any signal, anything like packets, and transmit them. Like here we have, in the x-axis, an increasing amount of bitrate. So you increase the streaming quality of the streaming video. And in the y-axis, we see the quality received. So the video will go through the network. This is a normal internet network, so it's not an Internet of Things scenario. And because it goes through packet losses and all sort of problems in the network, you will lose quality. So the idea is that if you increase the bit rate, you should get higher quality, obviously. Now, that's what you might think of. But it turns out that if the network, well, first of all, this is a non-linear process. So you can increase quality, you can increase bit rate up to a certain level, and then, of course, you can't improve anymore. So there is no point in transmitting 100 megabit per second video over the internet, because you will get the same, pretty much the same quality on the other end. But what is a bit more controversial is that when you do have high levels of packet loss and you increase bit rate, this is what happens to quality received. So you actually lose quality. And because high quality video is much more high bitrate video is much more susceptible to packet loss. So you see here that if you have a system that would be able to differentiate between signals, in this case would be able to understand that this is a video signal on a very lossy network, then you can do a lot of things to manage those signals better. Now if I go back here, because of those constraints on typical networks of layering, abstraction, insulation, and determinism, we just can't distinguish between signals. So if now you have not just human-generated signals, but also video, but also machine-generated video, and you don't differentiate among those systems, you might end up in a situation like the red line. And here is an example of a video. So if you take a video, you push it through a lossy network at 2 megabits per second. Because of the lossy network, you lose a lot of information. When the codec reconstructs the video on the other side, you have something like that, packetization. Now, if you compress the video, so if you do something as simple as compressing it down from 2 megabits to 700 kilobits, and then you send it, you look at the results. So in the first case, you have quality pretty much 15 dB, decibel. And in the other side, you're actually wasting fewer resources, less energy, less bandwidth, and you obtain better results. So it's a way for me to, I think, to try to make a case for having an Internet of Things communication network where you can make sense of signals. In the Internet of Things, by the way, you have signals from the physical world. So it makes absolute sense that the network or a network element decides when it's the best moment to transmit based on the type of data that's available, the quality of data, whether it's enough, whether it's relevant, whether it's an anomaly, and make transmissions based on the physical world. So putting these two things together, communication packets with physical signals, it's impossible today because of the way our communication systems are structured. And here I come with some conclusions, with some of the key points I wanted to bring to this audience today. Well, the first thing is, if we look at the numbers and the prospects, what is on the table right now, what companies hope to sell is in terms of the trillion things. This means 3 orders of magnitude in just 5 years or 10 years. That, I hope I convince you that this hitting physical boundaries is not to be negative, or, but this is hitting physical boundaries. So either we find a different way of communication, of communicating information, of moving information, because, by the way, having information and not moving it around is it's no use. So you need to move the information. So either we find different ways of moving information, or we reduce the amount of information, or we are just not going to go 3 orders of magnitude up. Maybe it's 1 order of magnitude instead of 3. I'm fine with that, because I'm not the one who is going to sell the sensors. So then I wanted to convince you, maybe I managed to convince you that this is more of a distributed prediction problem than what we have in current networks. So in current networks, you are able to predict things in advance and offline, and you don't actually do much more at real time. But what I think is very important is that in the Internet of Things network, we'll be able to make sense of the communications, build prediction models, anticipate transmission, understand the transmission, not in a centralized way, of course. That makes it even more interesting. I gave you just one example of how some network science knowledge, if you bring it in the right way into the IT context, you can actually obtain some nice results. But it's also a nice way to Internet of Things for us. It's a very nice way to play with network science in a more realistic way than it has been done so far. Rather than working on graphs and abstract values, you can actually build systems and see how to use network science and data science. So, and here is something else that I have totally escaped. Some major challenges. Some of these challenges, I put them down as challenges for the policymakers. They're actually also scientific challenges. So those of you working on privacy will probably shout and say, no, this is actually a theoretical research project, a problem. I totally agree with that. But at the same time, there's a policy problem, because interoperability, manufacturers don't want to build, at least at the moment, they don't want to build sensors that are interoperable, because they would lose their advantage to their competitors. So they're not pushing for standardization. Now, if you imagine an Internet of Things of non-standardized things, then the other problems of privacy and security will look like, well, not really big problems. You have a real mess if you don't have standardization at some level. And that can only be pushed through the policymakers. And by the way, there are activities, very active area, but it looks like the standardization process is much slower than the pace of technology. Now, looking at privacy, why did I, well, not talk about it? I think it's the same problem we have in the internet, but it's brought to a level that we might not want to ignore it anymore. So in the internet, we are ignoring the privacy problem. We sign all the terms and conditions. Anytime we download an app, we just sign to it. We don't care that we are giving away our data, because our data, what it is, it's just a video of our kids. Oh, relevant, but people are giving it away. It's not that sensitive. But if you imagine that you plug, pretty much like the Cisco video I showed you before, pretty much all your life is plugged in, and this data doesn't belong to you, it's not transparent to you, you don't know who has it, where it is, who is processing it, what they're doing with it. You might not be so comfortable if your data, your bio data goes beyond your doctor boundaries. But, so it's quite a big challenge for those of you who are working close to this area, I think. And security, you can, it has been demonstrated that people can hack pacemakers, they can hack cars. It has been done a few years ago, it's not even recent news. So you can imagine, the more you share, the more you get hacked. So, okay, the same problem with the internet so far. We have such a level of security here in this university that I couldn't connect my computer because of security policies and incompatibility between the policies set up, security policies set up in my university that are incompatible with the ones here. So I can't connect to the Wi-Fi network here, and we're talking about the Internet of Things. So it's quite, quite something. Security, it's confining, it's restricting us. So we either restrict ourselves and, or accept that we live in an unsafe and secure world. Now, I think, I didn't want to leave you with a negative tone here. I think there is an opportunity for lots of breakthroughs, especially, and I see IoT from the academic point of view as a fantastic opportunity to go back and study fundamental problems, which sometimes, I don't know if I can share with you, but we, in a technical university, sometimes we are brought to look at applications, solutions, demonstrators, short-term research. In a way, IoT is something that will force ourselves to go back to the fundamentals and look at some problems that we are not always able to have the luxury to look at. So we need to be prepared for some interesting paradigm shifts. I think I mentioned a few in between the lines, not explicitly, about networks. It's going from deterministic network to learning-capable networks. It's quite a big paradigm shift. It takes a complete rethink of the internet. So we might have to go along that way, or just cut our ambitions for the 1 trillion things. I think with that, I'd like to just invite you to probe further with some of the readings, some material you can find on my own page, and get in touch at a later time if you want to collaborate on any of these topics or just exchange opinions. But, well, since we're here, I would rather take some questions here rather than remotely, and then, okay. So that's all I wanted to share so far. Any questions? And by the way, I have a demo, a live demo. I will only do it in the end. Some people might not be interested. So maybe when we are done, I will go there. I'll show the demo. If you're busy with something else, you're free to go. No offense.